The Large Binocular Telescope is one of the world's most technologically advanced telescopes. Sitting atop Mount Graham, a 10,700-foot mountain in southeastern Arizona, LBT's unique design features two 8.4-meter primary mirrors mounted in tandem. New polishing techniques have brought both these mirrors to near-perfect uniformity, with surface variations within 1/2000th of the width of a human hair. When working together, they gather more light than any other telescope, and their combined focus yields images 10 times sharper than the Hubble Space Telescope. An innovative honeycomb design under the glass allows these lightweight spin-cast mirrors to remain rigid in mountaintop winds and to more readily adjust to ambient air temperatures. That means less blurring of the images of the deep space objects LBT is designed to capture.
We think this telescope's going to discover really interesting systems of planets around other stars. We think this telescope's going to map the dynamics of the inner regions of galaxies around massive black holes. We think this telescope's going to map the outer solar system and understand how our solar system was formed.
Because of the Earth's distorting atmosphere, it was once thought that astronomers would be unable to see these wonders through Earth-based telescopes, no matter how big their primary mirrors. But the development of adaptive optics changed everybody's thinking.
This telescope is going to be unique and first in having a full-time adaptive optics secondary mirror. What that means is that the light from the sky strikes this giant 25-foot primary mirror, which starts to bring it to a focus. Just after it goes through that focus, it will hit this adaptive secondary mirror. The secondary mirror reverses the path of the light and sends it back down toward the light analyzing instruments at the bottom of the telescope. However, that mirror is of a very special construction. The mirror is 36 inches in diameter and about the width of a few human hairs. It's 1.6 millimeters thick. It has 672 voice coil magnets glued onto the back, and we change the shape of the surface 1,000 times a second to compensate for the air boiling around above our heads. So that sharpens the image back nearly to the way that it would have been delivered with no disturbing atmosphere at all.
A bright star or a laser beam reads the atmospheric changes, and a computer translates that information so the sound coils can do their work. Dual mirrors and adaptive optics are just the foundation of the LBT's technological power. It's designed for adaptability and can be refitted relatively easily with new instrumentation as technology progresses. Initial instrumentation includes twin blue and red cameras for wide-field imaging, as well as nulling interferometry capabilities to spot distant planets, advanced spectroscopy devices, and a near-infrared imager and spectrograph called Lucifer. The LBT is one of the most complex research instruments in the world. The building itself is uniquely designed to adjust to the variety of instruments and to maintain critical alignment during complex rotations. Developed as an international project, LBT partners include an international consortium of scientists from the Arizona State University System, Italy's Istituto Nazionale di Astrofisica, Germany's LBT Beteiligungsgesellschaft, Ohio State University, and a private foundation, Research Corporation for Science Advancement.
It's going to be the scientific discoveries that this telescope makes that really count. That's going to be the bottom line when you look back over a telescope's productive lifetime. So the best discoveries are the surprises. I mean, right now we're facing an expanding universe, and an accelerating universe. That was completely unexpected a decade and a half ago. No one would have guessed that that was the best description of the cosmology, of the geometry of the universe. But we have the world's most powerful tool, and we're excited to start using it and to go there and see what we find.